November 8, 1942, Richmond, California, 1 minute past midnight. The clang of a massive steel plate echoed across Kaiser's Shipyard No. 2 as workers lowered the first section of keel into position. Floodlights bathed the construction ways in harsh white light, casting long shadows of the hundreds of welders, riv eaters, and fitters who had gathered for the night shift. This wasn't an ordinary Liberty ship launch. This was a challenge, a wager against time itself. Henry Kaiser had made a promise that seemed absurd even by wartime standards. His crews would assemble an entire 10,000-ton cargo vessel, complete with engines, boilers, deck equipment, and all systems operational, in less than 5 days, not 5 weeks, not 5 months, 5 days. The previous record stood at 10 days, and that had been considered miraculous. Naval architects called Kaiser's goal physically impossible. There simply wasn't enough time to weld the thousands of seams, fit the millions of parts, or test the critical systems. Yet, at 1 minute past midnight on that November morning, the clock started ticking on what would become the most extraordinary demonstration of industrial coordination in human history. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But to understand why this moment mattered, why building one ship in record time would echo through the decades that followed, we need to go back. Back to when American shipyards weren't building vessels in days but in months. Back to when welding itself was considered too dangerous, too unreliable, too experimental for anything as important as an ocean-going ship. Back to the crisis that made speed the difference between victory and total defeat. January 19, 1943. Portland, Oregon. The SS Schenectady sat peacefully at her dock, barely 10 weeks old. No storm threatened her. No torpedo had struck her hull. The morning was calm, the water smooth and glassy. Then, without warning, a sound like a rifle shot cracked across the harbour. Within seconds, the entire vessel broke completely in two. The hull split from deck to keel as if sliced by an invisible blade. Sailors scrambled as the bow and stern sagged in opposite directions. The ship's spine shattered while safely moored to the pier. Schenectady wasn't alone. That same winter, the SS John P. Gaines fractured apart in open water. The SS Esso Manhattan, a two-tanker built using identical methods, developed cracks so severe her crew abandoned ship in terror. Between 1943 and 1944, more than 1,500 Liberty ships reported catastrophic structural failures. Hull cracks, deck fractures, complete breaks. At least 19 ships broke entirely in half. 3 vanished at sea, disintegrating so suddenly they couldn't transmit distress signals. These weren't combat losses. These were ships destroying themselves from the inside out. The United States had wagered everything on the Liberty ship program. After Pearl Harbor dragged America into total war, the nation needed cargo vessels desperately. Hundreds of them, immediately. Traditional shipbuilding required roughly 8 months for a single vessel. The Maritime Commission couldn't afford that timeline. German U-boats were sinking Allied merchant ships faster than Britain could replace them. Every day without adequate shipping capacity brought the Allies closer to starvation and defeat. The solution seemed straightforward. Build ships the way Henry Ford built automobiles. Mass production. Assembly lines. Standardized components manufactured in parallel and brought together for rapid assembly. The design came from Britain, a simple tramp steamer called the Ocean class. Nothing fancy. No modern steam turbines, just reliable reciprocating engines that any maritime engineer could repair. No complex systems, just straightforward cargo holds that could carry tanks, jeeps, ammunition, food, and fuel. But the real revolution lay in the construction method itself. Liberty ships would be welded, not riveted. For centuries, ships had been assembled with rivets. Overlapping steel plates held together by thousands of metal fasteners, each one heated until glowing, hammered into pre-drilled holes, and secured with tremendous force. The process required highly skilled workers who had served years as apprentices. A riveter's accuracy and strength determined whether a ship's hull would hold back the ocean or leak like a sieve. The work was slow, labor-intensive, and demanded craftsmen who commanded premium wages. Welding changed the equation entirely. Instead of overlapping plates held by mechanical fasteners, welders used electric arcs to literally melt steel together. The seams fused at the molecular level, creating continuous joints without the weight penalty of overlapping metal. The process was faster, much faster. More importantly, it could be taught in days rather than years. Arc welding had existed since the 1880s, gradually refined over decades. By the 1930s, it had proven itself in building construction, pipeline work, and pressure vessel manufacturing. But the shipbuilding industry remained deeply skeptical. Ships faced stresses that buildings never encountered: wave action flexing the hull, temperature extremes from Arctic waters to tropical heat, saltwater corrosion attacking every surface, cargo loads shifting in heavy seas. Traditional naval architects argued that only riveted construction, proven over centuries, could withstand such punishment. The war forced their hand. Britain needed ships immediately and lacked the skilled riveters to build them fast enough. The United States, entering the conflict with virtually no modern shipbuilding capacity, faced the same constraint. Neither nation had time to train thousands of riveters through multi-year apprenticeships. But they could train welders in 10 days and put them to work on production lines that transformed shipbuilding from a craft into an industry. 18 shipyards were designated for Liberty ship construction. 6 of them were built from bare ground specifically for this program. The Oregon Shipbuilding Corporation rose on mudflats where no shipyard had existed before. The California Shipbuilding Corporation transformed a Los Angeles neighborhood into a maze of construction ways and fabrication sheds. Delta Shipbuilding in New Orleans expanded from a small repair facility into one of the largest industrial complexes in the South. And then there was Henry Kaiser. Kaiser was an enigma in the shipbuilding world because he had never built ships before the war. His background lay in construction, roads, dams, bridges. He had helped build the Hoover Dam and the Oakland Bay Bridge, projects that demanded logistical coordination on unprecedented scales. He understood mass production, labor management, and the critical path methods that kept complex projects on schedule. But he knew nothing about the centuries-old traditions of maritime construction, which turned out to be his greatest advantage. When established shipbuilders insisted certain things couldn't be done because they had never been done that way before, Kaiser simply ignored them. He hired automotive engineers from Detroit who understood assembly lines. He brought in construction managers who knew how to coordinate thousands of workers across multiple sites. He recruited industrial psychologists who studied worker fatigue and productivity. He even hired women and African Americans in large numbers at equal pay, a practice virtually unheard of in the 1940s South, because he cared about output, not social conventions. His Richmond, California shipyards became the most productive in the nation. By late 1942, Kaiser's yards were launching Liberty ships at an average of 42 days from keel laying to delivery. This was already considered miraculous. Ships that had taken 8 months now rolled off the ways in 6 weeks. The propaganda machinery celebrated it as proof of American industrial might. Newsreels showed Winnie the Welders, though they were actually welders now, transforming sheets of steel into ocean-ready vessels at speeds that would have seemed impossible just months earlier. The workforce itself represented a cross-section of American society thrown together by wartime necessity. Young women barely out of high school operated welding torches alongside elderly men who remembered wooden sailing ships. African American workers who had been systematically excluded from skilled industrial positions found themselves training white colleagues on specialized techniques. People with physical disabilities who had been dismissed as unemployable discovered they could perform critical manufacturing tasks that didn't require perfect mobility. Mildred Orpide exemplified this transformation. She had grown up in Louisiana's Bayou country near Houma, graduated from high school, and found work at the telephone company in New Orleans. The job paid poorly and offered no future. When she saw an advertisement for defense training in welding, she signed up immediately. The 2-month course taught her to strike an arc, control the molten pool, and run clean beads along steel joints. Upon graduation, she and her classmates were hired instantly by Delta Shipbuilding. The work was brutal. Summer heat in New Orleans, combined with the radiant heat from welding torches and the confined spaces inside ship hulls, created conditions that left workers drenched in sweat after minutes. The smell of hot metal, diesel fuel, and paint fumes pervaded everything. Burns were routine. Mildred once dropped a welding rod down her shoe, searing her foot so badly she carried the scar for life. Yet she and thousands like her took fierce pride in their work. They understood viscerally that every weld they completed, every seam they joined, every plate they secured brought American victory closer and brought their brothers, husbands, and sons home sooner. The welders developed an almost competitive perfectionism. Mildred later recalled that she could identify welds made by women versus those made by men. The women's welds ran smooth and neat, tight continuous beads that looked almost decorative. The men's welds were more careless, adequate, but lacking the meticulous attention to detail. She attributed it to having something to prove. The women knew they were being watched, judged, and evaluated constantly. They couldn't afford to produce mediocre work if they wanted to keep their jobs and prove that women belonged in shipyards. Delta Shipbuilding averaged 83 days to complete a Liberty ship, which was respectable but nowhere near Kaiser's pace. Other yards took even longer. The first Liberty ship, the SS Patrick Henry, had required 245 days to build, though that included constructing the shipyard itself simultaneously. By 1943, when production peaked, the average construction time had dropped to around 42 days. Nearly 3,000 Liberty ships were under construction or completed. 18 American shipyards working around the clock were producing an average of 3 ships every 2 days. The statistics were staggering. Each Liberty ship required approximately 250,000 individual parts, weighing about 14 million pounds total. The hull alone contained more than 30 miles of welded seams. Over 2,000 separate welds joined the plates, frames, bulkheads, and decks into a single structure. Every weld had to be sound, every seam had to hold. A single weak joint could propagate a crack that would tear the entire ship apart. And that's exactly what started happening. The early failures were dismissed as isolated incidents, poor quality control at specific yards, inexperienced welders making mistakes, defective steel from particular mills. But as more ships broke apart, patterns emerged that terrified naval architects. The failures happened in cold weather. They occurred in ships that had passed every inspection. The cracks didn't start in obviously weak welds, but seemed to originate in the base metal itself, then race through the structure at incredible speed. The physics behind the failures took months to understand fully. Steel is not a uniform substance. Its behavior changes dramatically with temperature. In warm conditions, steel is ductile, meaning it can deform and bend under stress without breaking. This ductility allows the material to absorb shock loads and distribute stress across its structure. But below a critical temperature, called the transition temperature, steel becomes brittle. Instead of bending under stress, it fractures like glass. The steel, used in Liberty ships, had a transition temperature around 40 degrees Fahrenheit. In the North Atlantic during winter, water temperatures often dropped below 35 degrees. The ship's hull, constantly bathed in freezing water, became brittle throughout its entire structure. Under normal circumstances, even brittle steel can handle moderate stresses. But Liberty ships carried an additional hidden danger: residual stress locked inside the welds themselves. When a welder runs a torch along a seam, the temperature in that zone exceeds 2,500 degrees Fahrenheit. The metal expands dramatically under that intense heat. As the weld cools, the steel contracts, but the surrounding cold metal resists that contraction. The result is residual tensile stress, permanently trapped inside the structure. These internal stresses can reach 30,000 pounds per square inch or more, concentrated in narrow bands along every weld. Riveted ships never faced this problem. Each riveted plate acted as a separate component with natural gaps and mechanical joints that prevented stress from building up continuously. If a crack formed in one plate, it reached the riveted seam and stopped. The overlapping joints and mechanical fasteners functioned as built-in crack arresters, but welded ships created continuous structures. A crack that began in one plate could race unchecked through hundreds of feet of welded seams with nothing to stop its propagation. The Liberty ships also suffered from design flaws that multiplied the danger. The British Ocean-class design, adapted for Liberty ship production, featured rectangular hatch openings with sharp 90-degree corners. These corners created stress concentration points where normal hull stresses were amplified 3 to 4 times. Every wave flexing the hull sent those amplified stresses racing through the corners. Combined with residual welding tension and brittle steel, these points became perfect initiation sites for catastrophic cracks. The SS Schenectady's destruction suddenly made perfect mechanical sense. She had been built during cold months using welding sequences that maximized internal stress. Her hull carried tens of millions of pounds of trapped tension distributed throughout the structure. When the Portland morning temperature dropped to 28 degrees Fahrenheit, the steel's brittleness increased sharply. The concentrated stress at a hatch corner exceeded the material's fracture strength. A microscopic crack formed, and within seconds, that tiny flaw became a rupture that tore through the entire vessel, splitting her in two while safely docked. The Maritime Commission ordered urgent investigations. Metallurgists examined fractured steel under microscopes, searching for defects in the material itself. Engineers recalculated stress distributions, checking whether the original design calculations had been wrong. Naval inspectors crawled through damaged hulls with measuring instruments, documenting crack, patterns and failure modes. Everyone searched desperately for the cause: bad steel, weak welds, design flaws, poor quality control. While investigations continued, more ships kept breaking apart. Sailors became terrified of their own vessels, knowing the hull beneath them might suddenly split open in freezing Atlantic waters with no warning, no time to launch lifeboats, no chance of survival. The miracle of mass production had transformed into a maritime disaster, and nobody could explain why ships built so fast were failing just as fast. The crisis threatened to derail the entire Allied war strategy. By mid-1943, the United States had committed to an invasion of Nazi-occupied Europe. Operation Overlord would require the largest amphibious assault in human history, supported by a supply line stretching across the Atlantic. Every tank, every artillery shell, every gallon of fuel, every ration, every bandage needed for the invasion would cross the ocean aboard merchant ships. If those ships kept breaking apart before reaching Europe, the invasion would be impossible. German propaganda seized on the failures with gleeful satisfaction. Reich Minister Joseph Goebbels broadcast radio messages mocking American disposable ships that destroyed themselves without any help from U-boats. The broadcasts claimed that German naval architects had warned that welded construction would never work for ocean-going vessels, and American arrogance had proven them correct. Every ship that broke apart validated German technical superiority and demonstrated that the United States lacked the engineering competence to challenge the Reich. But while German propagandists celebrated and American newspapers demanded answers, something remarkable was happening on the production lines themselves. The welders who actually built these ships, who worked inside the hulls day after day, who watched steel bend and twist under their torches, were beginning to notice patterns that the engineers had missed. The answer came from an unexpected source, not from the naval architecture departments at MIT or the University of Michigan, not from the Maritime Commission's team of experts in Washington. not from the British Admiralty's centuries of shipbuilding experience. The solution emerged from the welders themselves, the men and women who spent their shifts inside the steel skeletons, who felt the metal move beneath their torches, who understood through direct physical experience what the theorists had overlooked. Bessie Hamill worked the night shift at Kaiser's Richmond Yard No. 3. She was one of thousands of women who had entered shipyard jobs after the men went overseas to fight. She had been welding hull sections for 8 months by the time the crisis reached its peak in late 1943. 8 months was long enough to develop intuition about the material, to sense when something wasn't right, to notice patterns that others missed. Every night she watched her team follow welding patterns that made little mechanical sense to her. The standard procedure, handed down from the engineering office, instructed welders to start from the edges of plates and work inward, or to run entire seams straight from one end to the other in continuous passes. The engineers had calculated these sequences for maximum speed. Finish one seam completely before moving to the next. Keep the torch moving continuously to avoid wasted time. Maximize output per shift. But Hamill could see what those sequences did to the metal. As each weld cooled, the steel contracted, pulling and twisting the plates. She could literally watch the strain forming, the steel bending under her torch as internal stresses accumulated. When one section was finished and the next section was welded adjacent to it, those tensions became locked permanently inside the structure. It was like tightening the middle bolts on a car wheel before securing the outer ones. The result would be imbalance, warping, and eventual failure. Her foreman dismissed her warnings initially. She was only a welder, not an engineer. The welding sequences came from the design office, from men with university degrees and years of naval architecture experience. Who was she to question their expertise? But Hamill refused to let it go. The ships were breaking apart, and she believed she understood why. The engineering calculations were theoretically sound but practically wrong because they didn't account for the actual behavior of steel under the specific conditions of rapid assembly line construction. In November 1943, she requested a meeting with yard supervisors, breaking chain of command rules that could have resulted in her termination. She brought samples with her, test plates she had welded on her own time, using her own materials, each one demonstrating the results of different welding sequences. Some plates showed heavy warping and visible stress concentrations. Others, welded from the center outward using a more controlled sequence, remained flat and stable, with almost no distortion. The supervisors were skeptical at first, but their curiosity grew as they examined the samples. The difference was unmistakable. One supervisor agreed to observe the production line during Hamill's night shift to see the problem firsthand. What he witnessed confirmed everything she had claimed. The welders were unintentionally torturing the metal, forcing it to endure built-in stresses that would remain trapped for the ship's entire lifetime. Each cooling weld left residual tension within the steel. Because of the sequence used during construction, those internal stresses didn't balance out or distribute evenly. They accumulated in specific locations, particularly around hatch corners and other high-stress points. When those ships entered the freezing waters of the North Atlantic, the metal's brittleness, combined with the locked-in tension, created the perfect conditions for catastrophic cracking. Hamill's solution was remarkably straightforward. Begin welding from the center of each section and move outward, allowing the stress to flow toward the edges instead of concentrating in the middle. Alternate welding locations to avoid heat buildup in one area. Never complete long, continuous seams in a single pass. Instead, follow a balanced pattern that spreads the cooling stress more evenly across the entire structure. These weren't abstract metallurgical theories derived from laboratory experiments. They were hands-on insights from someone who worked directly with the material every night, who could feel the steel shift beneath her torch, who understood through tactile experience what the calculations missed. The difference between theory and practice, between what engineers designed on paper and what actually happened on the production line. By December 1943, Hamill's findings reached Henry Kaiser himself. He faced a difficult decision that would define his legacy. The Liberty ship program was already under congressional investigation because of the widespread cracking problem. Admitting that the issue stemmed from welding sequences rather than steel quality or design flaws meant acknowledging that nearly every vessel built so far carried fundamental structural weaknesses baked into their construction. That admission would require slowing production to retrain thousands of welders across all 18 shipyards. It would mean reorganizing the entire assembly system that had been optimized for speed above all else. It would involve admitting to workers, to the military, to Congress, and to the American public that the miracle production statistics had come at the cost of building ships with hidden structural time bombs. But the admission also offered a path forward. If the welding sequences were changed, if proper stress relief procedures were implemented, if future ships could be built correctly from the start, then the crisis could be contained. The ships already in service would require constant monitoring and careful routing to avoid the most dangerous conditions, but new construction could incorporate the lessons learned through such terrible cost. Kaiser didn't hesitate. He immediately ordered tests based on Hamill's recommendations. A full hull section was removed from the production line for experimental reconstruction. The same metallurgists and engineers who had spent months studying fractured ships now found themselves taking direction from a night shift welder who had never attended engineering school. For men who had built their careers on formal education and theoretical knowledge, the situation must have been humbling. But the war didn't care about academic credentials or professional pride. The test results shocked everyone involved. When Kaiser's team compared hull segments built using standard sequences with those welded according to Hamill's method, the contrast was undeniable. Instruments measuring residual stress showed that conventional welds contained internal tensions exceeding 30,000 pounds per square inch, concentrated in critical areas. Hamill's revised pattern spread those stresses across larger regions, with peaks barely reaching 12,000 pounds per square inch. The steel composition was identical. The welds themselves were chemically the same. The design hadn't changed. Only the welding order had been modified. Yet, the resulting strength improved dramatically. The hull sections welded using Hamill's method could withstand 3 times more stress before cracking than sections built using standard sequences. The engineers initially refused to believe the results and repeated the tests multiple times before accepting what the data clearly demonstrated. The true mechanics of the failures finally became clear. Steel possesses a crystalline structure that reacts continuously to temperature changes. When a welder applies heat along a seam, the affected zone experiences rapid expansion. As it cools, contraction occurs, but the surrounding cold metal resists that contraction. The outcome is residual tensile stress locked permanently into the structure unless the welding sequence allows it to spread evenly and dissipate naturally. The Liberty ships had been victims of what metallurgists call brittle fracture propagation. The carbon steel used in their hulls, though classified as shipbuilding grade and meeting all specifications, performed adequately in warm climates but changed dramatically in cold water. Below approximately 40 degrees Fahrenheit, its ductility collapsed. Normally, ductile metal can absorb stress by bending slightly rather than breaking. Cold steel loses that property and becomes brittle, behaving more like glass than tough, resilient metal. When brittle steel under high internal stress meets a sharp corner like the squared edge of a hatch opening, physics takes over with merciless efficiency. A microscopic crack begins to form at the stress concentration point. In ductile metal, the crack would stop as the material absorbed the stress through elastic deformation. But in brittle steel under heavy residual tension, the crack becomes a rapidly growing fracture. The energy trapped in the residual stresses drives that crack forward at accelerating speed. Sharp edges act as stress multipliers, amplifying the local stress threefold or more. The fracture then races through the hull, sometimes moving faster than the speed of sound in steel, tearing through the structure before any bulkhead can stop it. In hindsight, every Liberty ship failure followed this predictable pattern. built during cold months using sequences that maximized internal stress. Hulls carrying millions of pounds of trapped tension distributed throughout their welded structures. Service in cold Atlantic waters where steel brittleness peaked. Rectangular hatch corners providing perfect crack. Initiation sites. One moment of peak stress from a heavy wave or cargo shift, and the accumulated damage transformed into catastrophic failure. Henry Kaiser understood that the test results had implications far beyond his company's reputation. In January 1944, he faced a choice that would either prove his industrial genius or expose him as a reckless builder who had endangered thousands of merchant seamen. He ordered a complete redesign of Liberty ship construction procedures. More significantly, he began development of an entirely new vessel class that would incorporate everything learned from the Liberty ship disasters. The risk was enormous. German U-boats had already sunk more than 2,000 Allied merchant ships since 1939. The planned invasion of Europe, still months away in early 1944, would depend on the largest amphibious supply chain in human history. Every ship counted. Every week of delayed production meant Allied forces in Europe would lack ammunition, fuel, food, and reinforcements. The pressure to maintain production speed was immense. Kaiser was wagering that Hamill's welding sequence could be implemented successfully across all shipyards. That hull designs could be modified to eliminate stress concentrations without requiring complete redesign. That stronger, more resilient steel could be sourced and incorporated without causing material shortages elsewhere. That all of this could happen without significantly slowing the production rate that had made American shipbuilding the envy and terror of the Axis powers. His rivals thought he had lost his mind. Congressional investigators waited eagerly to condemn him if his gamble failed. The Navy's Bureau of Ships remained skeptical that a civilian contractor with no maritime background could solve problems that had stumped professional naval architects. Even within Kaiser's own organization, some managers argued for continuing Liberty ship production, unchanged while slowly incorporating improvements into later vessels. But Kaiser had built his career on bold decisions and personal conviction. He had constructed the Hoover Dam when critics said it couldn't be done. He had revolutionized shipbuilding when established yards said his methods would fail. He had hired women and minorities when social conventions said they were unsuitable for skilled industrial work. Every time, he had been proven correct through results rather than rhetoric. Kaiser's engineers began reworking the Liberty design systematically. Every right angle in the hull structure was replaced with smooth, rounded transitions. The rectangular hatch openings that had produced countless fractures were redesigned with broad curves, eliminating the stress multipliers that turned normal loads into crack initiation points. Deck and hull plate thicknesses were recalculated not to add weight, but to distribute stress more evenly with the new welding method. Internal frames were repositioned to align with natural stress relief zones instead of resisting them. The steel composition underwent modification as well. Kaiser's metallurgists developed a new alloy formula with significantly greater toughness at low temperatures. They slightly reduced carbon content and increased manganese levels. A small amount of nickel, rare and expensive due to its critical use in armor production, was added after tests proved that even 0.25% nickel content dramatically improved resistance to brittle fracture. The Maritime Commission initially resisted the additional cost, until Kaiser demonstrated that preventing just one ship's loss would offset the expense of upgraded steel for 50 vessels. In March 1944, the new steel specification gained final approval. The modified vessels were designated Victory ships, a name that reflected both optimism about the war's outcome and confidence that the engineering problems had been solved. The Victory ship design retained the Liberty ship's basic configuration, but incorporated dozens of improvements. Rounded hatch corners, crack-arresting features built into the framework, riveted joints at strategic locations to interrupt potential fracture paths, doubled structural frames in critical areas to provide redundancy. Most importantly, Every Victory ship would be constructed using the welding sequences that Bessie Hamill had developed through careful observation and practical experimentation. Her method became codified into detailed procedure manuals that specified the exact order of operations for every joint in the ship. These manuals spanned hundreds of pages, covering not just the sequence but also required heat management between welds, interpass temperature limits, and inspection protocols. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The challenge of retraining the workforce was monumental. By early 1944, Richmond shipyards employed over 90,000 workers. Thousands of them were welders who had learned their trade in intensive short courses designed solely to teach straight-line welding for maximum speed. Now they needed to master sequencing, stress control, and thermal management. Every welder had to unlearn habits that had been drilled into them as correct procedure and adopt new methods that felt slower and more complicated. Kaiser established welding schools within the shipyards themselves, pulling experienced welders like Hamill off the production lines to serve as instructors. Each welder received numbered sequence cards for every hull section. Weld number 1 goes here. Number 2 there, number 3 in this location. No deviations permitted, no shortcuts allowed. Supervisors moved constantly along the lines with detailed checklists, ensuring nobody skipped steps or reverted to old habits under production pressure. The prefabrication system expanded dramatically to support the new methods. Instead of welding huge sections directly on the construction ways where sequencing was difficult to manage and control, Kaiser's team divided Victory ships into smaller modules built in specialized workshops. A single bow section might contain 50 prefabricated subassemblies, each welded under controlled conditions using optimal sequences, then stress-relieved in furnaces before final assembly. This modular process allowed welders to begin at the center of each small unit and work outward exactly as Hamill had demonstrated, without the complications of working on an entire hull simultaneously. After welding, each module entered stress relief ovens heated to approximately 1,000 degrees Fahrenheit. The heat allowed the steel's internal crystalline structure to relax, releasing trapped stresses before they could accumulate. The modules were then cooled gradually in a controlled environment, preventing new stresses from forming. The actual ship assembly on the construction ways followed completely different logic from Liberty ship production. Instead of beginning with the keel and building upward layer by layer, Victory ships were constructed from multiple large modules, assembled simultaneously in parallel operations. The engine room, cargo holds, bow section, and stern were all built at the same time in different locations. When complete, these modules were hoisted by giant gantry cranes and joined together in one coordinated operation. The skeptics found immediate ammunition when the first Victory ship required 18 days to complete from keel to launch. The second took 16 days. Critics immediately labelled the project a failure, arguing that Kaiser had sacrificed his legendary production speed in pursuit of theoretical improvements. Newspaper editorials questioned whether the Navy had made a mistake trusting an industrialist with no maritime pedigree. Congressional investigators demanded explanations for why production had slowed when the war effort demanded maximum output. Kaiser ignored the criticism entirely. He focused on different metrics than his critics. The first 2 Victory ships showed 0 structural cracks after post-construction testing. Not fewer cracks than Liberty ships, not smaller cracks, 0 cracks, none at all. The hull plates remained flat and unstressed. The welded seams showed no signs of distortion or trapped tension. The ships were fundamentally sound in ways that Liberty ships had never been. By April 1944, Richmond Yard No. 2 had transformed into a precisely synchronized operation that resembled a vast industrial ballet. The yard no longer looked like a traditional shipyard, with vessels under construction at various stages of completion scattered across multiple ways. It looked like a highly organized manufacturing complex, with specialized zones feeding into central assembly areas where ships materialized with astonishing precision and speed. The process began in massive prefabrication sheds, where welders handled hull sections no larger than 30 feet in any dimension. Each section carried its own numbered sequence card detailing every operation. A bottom plate assembly might require 47 individual welds, each numbered and color-coded on the instruction card. Welders began at point 1, the geometric center of the section, and worked outward in spiral or radial patterns. Supervisors moved constantly with clipboards, verifying that no steps were skipped. After every 10 welds, each section entered a stress relief oven for heat treatment. This annealing process prevented the accumulation of residual stress that had doomed the Liberty ships. The steel itself arrived pre-cut and pre-formed from mills specifically retooled for Victory ship fabrication. Unlike Liberty ships, where workers cut and shaped steel on-site with acetylene torches and hydraulic presses, Victory ship components arrived ready for immediate assembly. Curved bow sections came pre-shaped to exact dimensions. Deck plates arrived with pre-drilled alignment holes. Frame sections came as pre-welded units ready for installation. All precision work occurred in controlled factory conditions rather than outdoors on the construction ways. This eliminated inconsistencies caused by weather, temperature variations, and the chaos of having hundreds of workers trying to occupy the same physical space simultaneously. The quality improvements were dramatic and immediately measurable. On May 12, 1944, Yard No. 2 completed its most ambitious assembly operation yet. 17 major modules comprising approximately 85% of an entire hull were aligned and positioned in just 11 hours. Welders joined these sections using the center outward sequence, but now they were connecting stress-relieved modules rather than introducing fresh internal tension into raw steel plates. The long-promised 5-day construction time was becoming reality through relentless optimization of every process. Kaiser introduced what he called the critical path method, a management technique that would later revolutionize project planning across all industries. He tracked which operations slowed production and which could proceed simultaneously without interfering with each other. If one task, like structural framing, moved faster than expected, while another, like pipe fitting, lagged behind schedule, workers were immediately reassigned to maintain even progress across all departments. Every delay, every schedule deviation, every bottleneck was recorded, analyzed, and addressed before it could compound. Each morning began with review meetings that examined the previous day's work and identified problems before they multiplied. Foremen from different departments coordinated their activities to avoid conflicts. Crane operators followed precise schedules, delivering components to workstations within 5-minute windows. Welders rotated on strict shifts, 30 minutes with the torch, 10 minutes rest. This pattern ensured consistent weld quality and reduced fatigue-related errors that were common during marathon welding sessions. The breakthrough arrived on June 27, 1944. The SS Benjamin Warner, Victory ship hull No. 23, was completed from keel laying to sea trials in 5 days and 11 hours. This wasn't a stripped-down prototype built for publicity. It was a fully operational, battle-ready cargo ship, equipped with defensive guns, complete electrical systems, a functioning engine room, radar equipment, and every weld executed under the new stress relief system. Her hull was flawless. Post-construction testing revealed stress levels comfortably within safe operating limits throughout the entire structure. During shakedown voyages in the Pacific, the Warner performed perfectly, enduring conditions that would have shattered an early Liberty ship. Heavy seas that would have propagated cracks through Liberty ship hulls merely flexed the Warner's structure within designed tolerances. The ship was strong in ways that transcended simple structural calculations. The 5-day Victory ship represented far more than a publicity stunt or a demonstration of raw production speed. It symbolized an entirely new understanding of how complex machines could be built when practical craftsmanship aligned with sound engineering principles. Bessie Hamel's observation, born from nightly experience watching steel respond to her torch, had grown into a comprehensive transformation of industrial shipbuilding itself. The Victory ships emerging from Kaiser's revolutionized production lines were fundamentally different creations, though to casual observers they resembled familiar cargo vessels performing the same missions as their Liberty ship predecessors. The improvements began at the molecular level with the upgraded steel specification and extended through every stage of design and construction. While Liberty ships had been emergency wartime stopgaps, compromised by the desperate need for speed above all else, Victory ships were true engineering solutions created to correct every flaw that had doomed their predecessors. The upgraded steel, known as killed steel because aluminum was added during smelting to remove oxygen, demonstrated vastly superior toughness at low temperatures. Laboratory testing revealed that the transition temperature where steel changes from ductile to brittle behavior had dropped from roughly 40 degrees Fahrenheit in Liberty ship steel to around 5 degrees Fahrenheit in Victory ship steel. This 35-degree difference meant that Victory ships retained their strength and flexibility in conditions that turned Liberty hulls into fragile, glass-like structures waiting for the slightest stress to shatter them. The higher quality steel cost approximately 8% more per ton, but its performance improvement was beyond monetary calculation. Every structural detail reflected the new understanding of how stress concentrated and how cracks propagated through welded structures. The rounded hatch corners, seemingly a minor visual modification, reduced local stress concentrations by more than 60% compared to the sharp 90-degree corners used on Liberty ships. Engineering analysis demonstrated that those sharp Liberty ship corners had created stress multipliers of 3.5 to 4 times normal hull stress. The Victory ship's smooth curves reduced that multiplier to under 1.8. In practical terms, this meant that a wave impact or cargo shift that would have initiated a crack in a Liberty ship simply flexed a Victory ship's hull within safe elastic limits, leaving no permanent damage. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.